In this lecture, we relate the trapezoidal rule to integration by parts, and in doing so, we will derive a long-established fact regarding the error when the trapezoidal rule is used to estimate the value of an integral. We state this fact as a theorem. In applying the trapezoidal rule, let t be the estimate for the integral of f over the finite interval from x equals a to x equals b. We are assuming a uniform partition with n subintervals so that the step size h, which is the length of each subinterval in the partition, is equal to b minus a over n. If the fifth derivative of f exists, then the integral of f is equal to t plus some constant c sub 1 times h squared plus another constant c sub 2 times h raised to the fourth power. C sub 1 and C sub 2 are both finite and depend on n. We consider the integral of f over the ith subinterval from x sub I minus 1 to x sub I, where the x sub i's are the partition points of the interval and x sub I is a plus I times h. We will apply integration by parts repeatedly throughout the proof of this theorem. According to integration by parts, if u and v are functions of x, then the integral of u dv equals u times v minus the integral of v du. We set u equal to f, so that du is f prime dx, and dv equals dx. We choose v to be equal to x minus m sub I, where m sub I is the midpoint of the interval from x sub I minus 1 to x sub I. So the integral of f on the interval is equal to u times v, or f of x times x minus m sub I, evaluated over the interval minus the integral of f prime times x minus m sub I. We plug in x sub I for x in the first quantity. X sub I minus m sub I is h over 2, since m sub I is the interval's midpoint. We first get f of x sub I times h over 2. We plug in this time x sub I minus 1. X sub I minus 1 minus m sub I is minus h over 2. So we subtract f of x sub I minus 1 times minus h over 2. We rewrite these two terms as h over 2 times the sum of f of x sub I and f of x sub I minus 1. This is the trapezoidal rule term for the ith subinterval. We call this t sub I. This other term must be the trapezoidal rule error for the ith subinterval. We apply integration by parts to this error integral. Applying and reapplying integration by parts is going to be a theme within the proof. For this integral, let u be equal to f prime, so that du is f double prime dx. dv is x minus m sub I dx, so that v equals half of x minus m sub I squared. The error integral becomes minus half of f prime of x times the square of x minus m sub I evaluated on the interval minus the integral of v, which is half, which we have just factored out, times the square of x minus m sub I times f double prime. We plug in the endpoints x sub I and x sub I minus 1 into f prime to get the difference between f prime of x sub I and f prime of x sub I minus 1. X minus m sub I is plus or minus h over 2 at both x sub I and x sub I minus 1, and its square is h squared over 4, which when multiplied to minus 1/2 gives us minus h squared over 8. We apply integration by parts to this integral with u equal to f double prime, so that du is f triple prime dx. dv is x minus m sub I squared dx, so that v is 1/3 times the cube of x minus m sub I. 1/3 times minus 1/2 along with a minus is 1/6, which is then multiplied to the product of f double prime and x minus m sub I cubed evaluated over the interval, minus the integral with v du. v is 1/3 times x minus m sub I cubed. 1/3 was already absorbed into 1/6, so that x minus m sub I cubed is all that's left of v inside the integral, and du is f triple prime dx. We apply the mean value theorem for secant lines to this quantity. According to the mean value theorem, there should be a value t sub 1 somewhere between x sub I minus 1 and x sub I, such that f prime of x sub I minus f prime of x sub I minus 1 equals f double prime of t sub 1 times h. We evaluate this part keeping in mind that x minus m sub I is h over 2 at x sub I, and is minus h over 2 at x sub I minus 1. We get this quantity. We apply integration by parts to this integral, with u equal to f triple prime, so that du equals f quadruple prime dx. X minus m sub I cubed dx is dv, so that v is 1/4 times x minus m sub I to the 4th power. And this is the result. We copy these three terms and evaluate this expression at x equals x sub I, and subtract its value at x equals x sub I minus 1. X minus m sub I is plus or minus h over 2 at the endpoints, so we should get this result. Then we have the product of minus 1 over 24 and the negative of this integral. We can factor out h cubed from these two terms, so that we rewrite the sum of these two terms as some constant k sub 1I times h cubed. We apply the mean value theorem to this difference. There should exist a value t sub 2 between x sub I minus 1 and x sub I, such that this difference is equal to f quadruple prime of t sub 2 times h, so that this expression is equal to minus h to the 5th power over 384 times f quadruple prime of t sub 2. Let k sub 2i be equal to minus f quadruple prime of t sub 2 divided by 384, so that these are the first three terms on the right side of the equation. We will find a bound for the absolute value of this integral. The absolute value of this integral should be less than or equal to the integral of the absolute value of f quadruple prime times x minus m sub I raised to the 4th power. X minus m sub I raised to the 4th power is already non-negative, so we don't need to apply the absolute value to it. X minus m sub I to the 4th power is also less than or equal to h to the 4th power on the interval. And so, replacing x minus m sub I to the 4th power with h raised to the 4th power, we obtain a quantity that is at least as big. We take h to the 4th power out of the integral since h does not depend on x. We apply the mean value theorem, this time for integrals, to the integral of the absolute value of f quadruple prime. According to the mean value theorem for integrals, there is a value t sub 3 between x sub I minus 1 and x sub I, such that the integral of the absolute value of f quadruple prime equals the absolute value of f quadruple prime of t sub 3 times h. With a factor of h multiplied to h to the 4th power, the absolute value of the integral of f quadruple prime times x minus m sub I to the 4th power is bounded by the absolute value of f quadruple prime of t sub 3 times h to the 5th power. Therefore, the integral of f quadruple prime times x minus m sub I raised to the 4th power divided by h to the 5th power is finite, because its absolute value is bounded by the absolute value of f quadruple prime of t sub 3. Let a sub I be equal to 1 over 24 times the integral of f quadruple prime times x minus m sub I raised to the 4th power all over h to the 5th power. Then the integral of f on the ith subinterval equals this sum. Remember that this is just for the ith subinterval, so we sum over all the n subintervals, so that the integral of f from x equals a to x equals b equals this sum. Let k bar sub 1 be equal to the arithmetic mean of the k sub 1 i's, so that the sum of the k sub 1 i's equals n times k bar sub 1. We take one of the h's from h cubed and multiply it to n. h times n is b minus a, so that the order h cubed term in the summation is b minus a times k bar sub 1 times h squared. We set c sub 1 equal to b minus a times k bar sub 1. This gives us the h squared term in the theorem. Let k bar sub 2 be the arithmetic mean of the k sub 2 i's, and let a bar be the arithmetic mean of the a sub i's. And so the sum of the k sub 2 i's times h to the fifth power plus the sum of the a sub i's times h to the fifth power equals n times the sum of k bar sub 2 and a bar times h to the fifth power. Out of this, we get something very similar to the k bar sub 1 term. We get b minus a times k bar sub 2 plus a bar times not h to the fifth power, but h to the fourth power. We set the coefficient of h to the fourth power equal to c sub 2. So we have the h to the fourth power term in the theorem. The sum of the t sub i's, of course, is the trapezoidal rule estimate t of the integral of f from x equals a to x equals b. This concludes the proof of the theorem.